Good day, everyone. I am Alejandro D. Caranto from the College of Engineering, Tarlac State University, Tarlac City, Philippines. I'm going to present to you this research entitled Designing a DC Electricity Electroculture Circuit for Plant Stimulation. The introduction of electroculture in a garden or farm is another innovative method applying electrical currents to increase harvest. This practice has recently become more accepted amongst planters and researchers. The understanding behind electroculture in plants is that immediate electrical currents can be advantageous. The electrical inducements have an effect on plants in a variety of techniques. Tests and trials have showed that electrical currents can promote plant growth as well as improve its produce. Applying these electrical currents promote plant development, which lead to larger and healthier plants, resulting in higher yields of fruits and various crops. Aside from that, it can also decrease the need for synthetic fertilizers. That is why it is environmentally friendly and sustainable. This study aimed to design a DC electricity electroculture circuit for plant stimulation with the specific objectives. One, to design an electronic circuit of DC electricity electroculture with an ideal current of 300 milliamperes, 400 milliamperes, and 500 milliamperes. Two, to analyze the electroculture circuit design using simulation application. And three, to determine if the electroculture circuit ideal load current versus the simulation measured load current falls within the positive negative 10% tolerance. The research design used in this study is research and development, specifically the design method. Research and development is a set of inventive undertakings in creating innovative products or skills, as well as enhancing the potentials of existing ones. To design a DC electricity electroculture circuit for plant stimulation, the following steps were done: planning, development, and analysis. Firstly, the planning stage involves what prototype of circuit to be used, as well as the equipment and materials needed to design the electroculture circuit. The researcher utilized the basic circuit for constant current regulator as a reference to conceive the electroculture circuit. Secondly, the development stage involves the step to sketch the schematic diagram and compute for the values of its electrical parameters using Ohm's law equation. Finally, the analysis stage uses the simulation application software to verify the accuracy of the electronic circuit. The current flowing through the copper rods has been measured using the virtual ammeter to verify that the ideal value versus the simulated value falls within the acceptable positive negative 10% tolerance. The results were, in figure 1, it shows the DC electricity electroculture circuit with unknown R sub 1 and R sub 2. Figure 1 shows the DC electricity electroculture circuit for plant stimulation. It is simply a current regulator with a supply voltage of 9 volts using bipolar junction transistor, Zener diode, and 2 resistors. The transistor Q1 has a beta current gain of 35 to 300. Now, in this circuit, the researcher has used a beta current gain of 100. The Zener voltage, V sub Z, is 4.704 volt, and the Zener current is 61.01 milliamperes. The two resistors, R sub 1 and R sub 2, are unknown. The resistance value of the resistors will determine the current that will flow on the copper rods. Now, figure 2 is an electroculture circuit with an ideal load current of 300 milliamperes, showing the value for the computed R sub 1 and R sub 2. R sub 1 is 67 ohms, while R sub 2 is 13 ohms. For figure 3, electroculture circuit with an ideal load current of 400 milliamperes, the computed value for R sub 1 and R sub 2 are 66 ohms and 10 ohms respectively. For an electroculture circuit with an ideal load current of 500 milliamperes, the computed values for R sub 1 and R sub 2 are 65 ohms and 8 ohms respectively. Now that we have computed for the value of R sub 1 and R sub 2, it's time for the analysis of the circuit. Simulation software is founded on the course of prototyping a factual value with a set of mathematical equations. It is a computer program that lets the user view a process with the use of simulation. This is also used in designing an electronic circuit so that the final outcome will be accurate to design specifications as possible. To analyze the design, each circuit with an ideal load current of 300, 400, and 500 milliamperes have been constructed in the simulation workspace. Then, an ammeter was used to simulate the current flowing in the copper rods. The results were, for figure 5 shows the simulation of the electroculture circuit with an ideal load current of 300 milliamperes. And the measured value is 294.362 milliamperes. Next, figure 6 shows the simulation of electroculture circuit with an ideal load current of 400 milliamperes. The measured value is 379.579 milliamperes. While figure 7 shows the simulation of electroculture circuit with an ideal load current of 500 milliamperes. The measured value is 470.598 milliamperes. Now, to compare the two, the ideal load current versus the measured load current, Table 1 shows the ideal load current in comparison with measured value. Table 1 shows the ideal load current of 300 milliamperes, 400 milliamperes, and 500 milliamperes in comparison with the measured load current. For the ideal load current of 300 milliamperes, the measured value is 294.362 milliamperes, which implies that it falls within the positive negative 10% tolerance value. For the ideal load current of 400 milliamperes, the measured value is 379.597 milliamperes, which implies that it falls within the positive negative 10% tolerance value. For the ideal load current of 500 milliamperes, the measured value is 470.598 milliamperes, which implies that it falls within the positive negative 10% tolerance value. All the three values falls within the tolerance value. So for the conclusion and recommendation, because each of the measured load currents compared with the ideal load current fall within the positive negative 10% tolerance value, therefore, it indicates the design of a DC electricity electroculture circuit for plant stimulation will work efficiently. It is now ready for fabrication, then it can be utilized in plant stimulation. That's all. Thank you very much.